We are continuing our deep dive down the network stack. So if we remember our network stack, we had our layers model, and the application is delivering data via the transport layer to the network layer. Today we're looking at the transport layer and in specific transmission control protocol. It's the big one really, it's probably the most complicated of them. So let's have a look at the job it's got to do. Let's motivate what we've got to do. Let's just remember back to the last one we were doing, we did user datagram protocol. And the job of user datagram protocol is very similar. My diagrams always start like this. We have our poorly drawn laptop, we have our poorly drawn server, and we have the internet drawn as a cloud. Hooray. Now, we've got some applications running on our laptop, some applications running on the server, and we want to get data from the app through to the other app. We want that data to go through the internet. It's got to get between the right program on this laptop and the right program on this server. But we've got the wilds of the internet, so anything can be in here. It's not necessarily a benign environment for our data, right? Things can go wrong.
Those old maps used to say, here be monsters.
Oh, yeah, exactly. Here be monsters. Let's have that. That would be nice. So what we're going to do, let's abstract that picture a little bit, and let's imagine our application is sitting here, and what we want is a nice, reliable pipe that we can pour bytes into. So bytes in here, bytes out here. But actually, what we've got underneath is a leaky pipe, which we can have data loss, data corruption, and packets might get out of order. And the job of our transport control protocol sitting here and sitting here, so it's only sitting on the end devices, its job is to pretend that this manky, leaky pipe that's corrupting and dropping our data, pretend that doesn't exist and pretend we've got a nice, reliable pipeline. Last time we introduced the concept of a port, which tells us which application to come from and go to, but now we're going to need a lot more. A little apology before I start, because with UDP, I could explain more or less everything, right? With TCP, I have not a hope. If you want the full gory details, it would be RFC 793 was the old one, but actually I discovered 9293 obsoleted it in 2022. Shows what happens if you don't stay current. The RFC, the request for comments, is what we internet people take as our kind of Bibles of how these things work. So we're going to need two little mechanisms. We're going to need what we call a state machine to track at each end where we're up to and what we're doing. And we're going to stick a header onto our data. So we've got our big pipe of bytes that we want to send. I'm going to chop them up into little bits. And each of those little bits, we're going to take that data and stick on the front of it a header. And this beautiful bit of ASCII art, lovely, shows us what those bits we must stick should be. So the way to read this diagram is, this is the 0th, 1st, 1st, 2nd, 3rd, 1th. The 0th, 1st, 2nd, 3rd bits on the header, like normal people, computer scientists always start counting from 0, not 1. So the first 16 bytes are the source port, the application it's coming from, the destination port, and so on and so on. I'm not going to explain every single bit of this. There's some things we'll need to look at. There's a sequence number and an acknowledgement number, for example, which we'll get onto later. There's a bunch of flags that do different things. So these little things are just zeros and ones that tell us, is this particular packet an SYN packet? Is this particular packet an FIN packet? And we'll talk about what that SYN, FIN, etc. means. There's other things in there. There's a checksum. And we talked about that with UDP, so we know what it is. A checksum's our way of telling, has this been corrupted? Now, we're going to need several mechanisms. The two that I'm going to really talk about today are creating a connection and getting reliability. So let's start with that first one. Because this protocol needs to track state, we need to create a permanent structure. Well, we need to create a structure in the computer's memory that's going to stay there for the duration of us sending data to and from that computer. So we are going to need to have something that's living on the receiver and on the sender, and that structure, we'll call it a socket, is going to stay there while we are sending data. So what we want to do is create a socket here, connect them up, and those sockets connect directly into the application. Bam, bam, bam. So the first thing we're going to need then is a way of saying to our computer, can we set up a socket between these two? It's what we call the three-way handshake. It's a classic bit of computer science because we need three, two will not do us. We need to say hello, and that hello is the SYN, the SYN packet. So the person wanting to initiate the connection sends a packet with this SYN flag sent, so SYN. You, the receiver, send back your own. So SYN is kind of synchronized, I want to set up a socket with you. The receiver needs to acknowledge the presence of that, so it's going to send back an ACK, but that ACK is also SYN because it's going to say, I would like to set up a socket with you. Then we send back an ACK to acknowledge that socket. So once you've had SYN that way, SYN ACK back that way, and an ACK back that way, now we've got a socket pair set up. And that socket pair, so if I put bytes into the socket at my end, they should be spat out at your end identically in the right order with no bits going missing. In between, those bits can be corrupted, but we've got a checksum to count for it. But they can get out of order and they could be lost. Now that's the next problem. We deal with them in the same way. So I think I've asked you this question before actually. How might we deal with the idea that a whole packet can get lost?
Well, presumably they all have to kind of have some kind of sequence number on them.
Precisely this. So we need a sequence number. So we've got our sequence number. And we also need a receipt back, right?
Receipt. An ACK, another
ACK, yeah. So an SEQ and an ACK. These are the things that's going to do the job of ensuring that nothing is lost. So we're sending out our packets. We're sending out our sequence numbers, and the packet has a number indicating a sequence. I'm going to skip over some magic there because the sequence number doesn't begin 1. It's actually genuinely important. It begins with a random number that's impossible for anybody to predict. For security reasons, why? I won't go into the magic of how that happens. The application, when it receives a sequence number, is going to send an acknowledgement number, and that acknowledgement number is saying the packet it wants next. So it's saying, okay, I have seen packets 4, 5, and 6. Can I have packet 7? Now, here's where we get into some difficulties, shall we say, or not difficulties, but some things that need to be resolved. So let's imagine I've sent, now I'm going to number these from 1. That's not really how that numbering works. That numbering is actually a byte numbering, yeah? So the sequence number is telling you the bytes that are being sent. So it wouldn't really start for 1. But let's imagine I've sent over packets 1, 2, and 3, and they get to the other end, but oh dear, 2 is gone away. Maybe it got corrupted. Maybe it was one of the routers on the way was full, it got dropped. So now use the application, you get 1, we're sending back an acknowledgement, and that acknowledgement is the acknowledgement associated with packet 1. Now I get 3, I'm not going to throw it away, but I can't give it to the application, right? Because then our messages got out of order. Now, I'm going to send back ACK1 again. Yeah? And by sending back that ACK1, I'm saying, I've got some data for you, but it's not the data I really wanted. I've got something, and I've just realized my data's flowing this way now from the laptop, but never mind. Now the laptop realizes, right, he sent me back ACK1 again. Something's not gone right. And you can send some extra data, and eventually you're going to realize, all right, he's after data 2. He's after the piece of data 2. There's a lot of subtlety in there, and I'll deal with those in the next video of exactly how the ways that this can work. We're going to also need some kind of timeout mechanism. Again, the subtleties in here. So we're going to need to say, well, I was hoping to see ACK2, but I haven't. I'm going to wait a little bit of time, and if we haven't seen it, we're going to send packet 2 again. We're going to assume it's lost. There's other clues we can use. So we can use the fact that if we see ACK1 several times, we call that a duplicate. So I see ACK1, I see ACK1 again, I see ACK1 again. And you don't have to be Sherlock Holmes to detect we've got a problem, right? We say, we've got ACK1. We call it a triple duplicate if we've seen it once and 3 more times, and then we go, you know what? Packet's lost. I'm going to send it again. Bam. Send off another copy of 2. So now we've got a mechanism whereby we can get rid of our corrupted packets. If our packets have got out of order, well, actually, let me illustrate what happens to be out of order, because I haven't done that yet. So let's imagine our tardy packet 2 that got lost. We've resent it. It shows up. So packet 2 shows up. We can pop it in here. And now we don't need to acknowledge 2. We can actually send out the ACK associated with 3 to say, not only have I got 2, happy day, I've got 3 as well. So, and again, technically the acknowledgement sent is the acknowledgement requesting the next byte. It's not really numbered 3, but it is the acknowledgement associated with, I have all the packets up to 3. Yeah. So, we've got our out of order, we've got our corruption, we've sort of got the rudiments of a method for sending data reliably. We have got some problems remaining, and one of those problems is, if we think about this, it's going to be real slow, right? Like if we were having this conversation and I required you to acknowledge and say yes after every word, I'd go, hey,
yes,
Sean,
yes,
we
yes,
are
yes,
going to talk about TCP, and the conversation becomes very slow. If I get an acknowledgement for every packet and send a packet and get an acknowledgement, it's just going to be painfully, horribly slow. So we need to send the packets together in bunches. We call them flights. And in the next video, we'll talk a little bit about how that works. But we need some mechanism of saying, all right, I am good. I'm happy to say that this network can have 10 packets in flight at once before I get any acknowledgements at all. And we need to kind of probe the network and say, can you take 100 packets? Can you take 1,000? Can you take 10,000 packets? We need to know how big our network is. This is something we call the window. There's a window size on there. Hopefully it's not that window, it's a different one, but that's nothing to talk about. With TCP, we need to think about security. So there's a little aside here that's quite interesting, because even in just, we always need to be thinking, how can this go wrong? How can it fail? How can it be hacked? So even in just that simple SYN-ACK mechanism, no matter how we do it, there's a little hack in there. There's a little denial of service. You might remember Mike did a video about slow loris. So it's a lovely little attack, and slow loris is an attack that kind of slowly uses up all the resource on a web server. With SYN-ACK, we've also got a potential hack, what we call a SYN flood. Because these SIM packets are very little. They're carrying no data. They're just basically just a header and saying, you know, I would like to establish a connection. It's almost nothing to them. Very, very tiny packet, yeah? And the server computer needs to say, okay, they want to set up a connection. I'm going to reserve a socket. I'm going to send back a SYNAC. It's reserved some memory. It's reserved a little bit of its resources. It's you know, it's like if I ask you for a high five and then leave you hanging. So the SYN flood, if I send out loads of these little tiny packets, I'm just nibbling away tiny bits of memory off your computer. If I can get 100 or 1,000 or a whole botnet to do that to you, that SYN flood attack nibbles away all of the resources of your computer. Suddenly, you can't serve your legitimate customers. You're too busy dealing with my botnet throwing 1 million SYN packets at you. It's quite an old school attack. There's lots of ways of mitigating that nowadays. But I think it's nice to just realize that even in describing something very, very simple, we immediately see a kind of security hacking hole that we need to work our way around. And that's the kind of bad world of the internet we live in today. But with this, we've got all of our mechanisms. I didn't talk about closing a connection. That's the FINAC. We've actually done a video on that, the goodbye problem. So Green General's sitting on the hillside going, what can I do? But these are the basic mechanisms behind TCP. This will get us reliable transport. If we fiddle with that window size carefully, we can get it sending efficiently. So in the next video, though, I want to show you some examples and dig a little bit into the kind of ugliness and the difficulties of doing this in the real world. What you can be sure of is you've sent this many packets. Well, as far as you're aware, they're out there in the world. You don't know how big the network you're connecting to is. Because remember, you've got to connect to everybody, right? They may be in Melbourne, they may be in Beijing, they may be just next door.